in a similar way, this is called a non-resonant process, because now you have a situation where you don't completely absorb the entire incoming electron. Okay, the incoming electron beam, as in scanning electron microscopy, you send in a fast electron beam. You just excite, right? The electron beam just need to transfer some energy into your material. Okay, this is called non-resonant transition. You just basically bump off some energy. Your incident electron still keep going on in its own merry way. And you could create an excited state like this, right? With one electron missing from your core hole, right? Once you create this situation, then X-ray fluorescence could also occur, okay? And this is in fact what people recognize, and this is and turn it into a supporting technique called energy dispersive X-ray analysis, or EDAX, right? Commonly known as EDAX. And this EDAX technique is in fact like this. It's a radiation decay of the filling up this de-exciting this excited state back into the ground state. And of course, this photon, X-ray photon that emitted, can be used to identify the element. So this is how SEM, a nano technique, SEM imaging technique inherently, can be used as a way to do elemental analysis using X-ray fluorescence. Now the other way that I will talk about today to de-excite this excited state is called the OJ process. Okay, so you have this OJ electron created from here. In order to fill this hole, one of the electrons can fill the hole, and then you still have a lot of energy, because remember the absorption of the photon is a resonant process. You absorb one complete photon. You cannot absorb part of the photon, right? Because photon is h mu. You either absorb all of them or you don't absorb. Okay, so you absorb the photon, and you still have this entity still have a lot of energy left, and in order to release this energy, it can release the second electron, and this second electron is called the OJ electron. And the OJ electron, the location, how fast the OJ electron is emitting, depends on the energy difference. Again, depends on the energy differences. We'll come back to this a little bit later on when we talk about surface exam, and we need to use something called the OJ process to select out the process related just to the surface, not to the bulk. So we were talking about last day about these interference effects. So in the case of XAP, very quickly, is that you create a core hole in here, right? You have a photoelectron process. You absorb the photon, the photoelectron wave come out, usually emanating as a spherical wave, so-called S wave. And this S wave bounce off your neighbors, right, in these ladders. And this interference effect affects, cause interference in the absorption cross-section, in the absorption cross-section of your intensity that you see. Okay. So what you got is that you have a think of it as you can have a X-ray coming in, right, with I naught intensity, original intensity, pass through your material, and you measure the intensity gets passed through. So it's a classic absorption spectroscopy, right? You have done this in UV absorption spectroscopy, or in the case of X-ray spectroscopy, you can use if you have powder or nanomaterial or callus, you can just use Scotch tape. Just tape your really literally you can buy some Scotch tape, and essentially just sprinkle your powder, nano powder or callus onto that Scotch tape, and let the X-ray pass through, and then some detector and somehow measure the intensity of that X-ray, and you're done. Okay, so it's a rather straightforward looking technique. And you got very similar information that you have. So you have initially you have excitation. Basically, you have ground state to excitation transition that usually give you peaks, right? As in UV absorption spectroscopy. But if your photon energy, this h mu here is high enough, you have enough energy to ionize it, actually eject one of the electron in the energy level out to the continuum, right, to create an ionic state. So now you created a charged state. And when that happens, you have absorption edge. You got things like this, okay? And whenever you see a little bump like this, that indicates you have an ejection of the electron. You create an ionic state, okay, in the absorption spectroscopy. And then, of course, there's a little feature on top. If you look very closely, so if you look at this little edge in here, you see this little feature on top, also this little peak on top. These near structure, so-called near structure. And then if you look further down, about 50 electron volt, you see a tiny little amount of wiggling. Okay. Originally, when people discovered this defect, they thought, oh, these are just noise because these wiggles are less than 5%, right? So it's a general rule when you do experiment. 10% effect is very easy to see. 5% effect is exponentially difficult to see, and 1% effect is almost extremely difficult to see, right? Because your instrumentation has to be so good that you have to take care of the fact that it's not an instrumental effect. So because most of the electronics has to be so good that it has to be stable to within 1% if you're trying to measure 1%. So that's very, very difficult experiment. So you are here, we are looking for under 5% effect. With most of the wiggle, the intensity above a background. So here I'm trying to draw a blue line and an average background going through the middle of these wiggles, you see. And the height of this wiggle above the blue line is less than 5%. In most cases, it's less than 1%. So you're talking about noise level spectroscopy. And this is very difficult because now you remember when you're doing this kind of experiment, you usually have discrete counting statistic. You're counting something. And whenever you're counting something, the noise goes as square root of n, right? So this is normal counting statistic, your error. So you have to have large enough n, the number of detection has to be large enough in order to reduce the error down. So it is not a so simple experiment when they first started to do exact experiment in the mid-70s and late 70s. And what they found, rather interestingly, so there are two areas of interest. One is that they found this little peak, rather sharp peak near the absorption edge. So this is my absorption edge. And then these wiggles, and some smart guy discovered that, well, this wiggles really depends on a couple of things. There are two things you can say about this wiggle. One is that how strong are these wiggles? The intensity, how much above this flat background that I draw. Okay, so the intensity of the wiggle seems to depend on the number on the coordination number of you have. In other words, if you have a 6-member coordination number is 6, then the intensity of this wiggle is larger than a coordination number of 2, that's just 2 neighbors. So here you have the dashed line, for example, correspond to this wiggle coming from a material with 6 coordination number of 6, and compared to the solid line, which have a coordination number of 2. So that's one thing that people notice. Second thing they notice is that the periodicity, right? This, if you point out the peak location of these, this periodicity seems to depend on the bond length. Okay, so the larger the bond length, the closer are these peaks. They don't seem to lie in a regular fashion. It's sort of semi-regular fashion. They have a wiggle, but the wiggle seems to be spreading out. But if you look at shorter wave bond length, these wiggles are spreading out further than the one with longer quantum. So two recognition that you will find. And as I said before, they use, I'll talk a little bit about this. This really, you notice that when you do this kind of spectroscopy, you need a tunable photon source.